volume and surface area because I thought that was the next section. I forgot there's angles in between.
Okay, so anything with angles I should sort of ignore?
You should not feel bad if you skipped it and we're like, ugh.
Okay, never mind then. I got pretty far.
Yeah. Okay. So the next section is angles within 3D solids. So again, we're going to be using calculation triangles to solve these sorts of things. Just a piece of vocab. When we talk about the angle that like a side makes, like an edge makes to a side, you're just talking about the other arm of your angle is any line that's in the same plane as that side. So like, here or here or here. If you think about it in 3 dimensions, though, it's all the same angle, right? Doesn't matter where that line is drawn. It's still like the same angle. That's just like a piece of vocab. So we might be asked to find angle measures like the angle between the base of the cone and like its slant edge. So the angle we're talking about there is this angle ABC. Yeah, apparently the Jackson 5 is here to say hi. How's it going, guys? Where's little Michael? All right. Or you might be able to ask to find the angle between the height of a pyramid and its edge. So that's this angle ACB. Or you might ask to find the angle between a line, that's an internal diagonal it looks like, and the base of the prism. So that's this angle FAC. Oh, FA is is an edge. I don't know why it said line. It probably should have said edge, but whatever. Oh no, it's not. That's a diagonal on the top. This is like a wedge. This 3D shape here that looks pretty convoluted. It's like a doorstop, like a wedge. So this side FA is like a diagonal on the top of the wedge. So let's do a couple of examples for the triangular prism below. Another wedge. Calculate the height EB, and then find the length of the line DB and the length of the line DE. And then we're going to find the angle that DE makes with the base of that prism. So first things up is EB. The calculation triangle I would use is EBA. Since I know AB is 15, I'm given that angle EAB is 21 degrees. I can calculate EB by using tangent. So I can say tangent at 21 is equal to EB over 15. And when I grind that through, I get that EB is 5.76. Part B asks us to find the length of that line DB. So what I would do here is I'm going to use the triangle. I forget if I'm going to do DBC or if I'm going to do DAB, but I drew both of them. Ha! Fooled you both and myself. I can then just use the Pythagorean theorem to find DB. So 15 squared plus 23 squared square rooted is DB, or 27.46. If I know DB and I know EB, I can certainly find the length of ED, which was next, just by doing the Pythagorean theorem again. Everybody's okay there? And then the last thing we're looking for is this angle EDB. If I know the 3 sides of the triangle, though, I can calculate that angle EDB by just doing something like tangent inverse, opposite over adjacent. And that spits out my answer. Now for this particular problem, did it really matter whether I used tangent or sine or cosine? No, because we knew all three sides of the triangle. So like, as long as you put the stuff in the right places, you could have used any one of those trig functionaroonies. I wouldn't have used any of the reciprocal ones because they're not built into my graphing calculator. You could have, but like, it's kind of a hassle. I don't know why you'd want to. All right. Another example. A cylindrical drum contains a stick that fits the diagonal exactly. If the radius of the drum is 5.8 centimeters and the height of the drum is 15.8 centimeters, calculate the length of the stick and then the angle that the stick makes with the side of the drum. So the length of the stick, let's do that part first. We'll use the calculation triangle ABC. We know that BC is 15.8, and we know AC is twice the radius. So that's 11.6, and then we can just Pythagorean theorem that guy up to get 19.6 for the length of our stick. Thrilling, I know. In part B, it asks for the angle that the stick makes with the side of the drum. So are we talking about the angle ABC or the angle CAB? So the side of the drum and the stick is talking about this angle here, right? So that's the angle ABC is what we're looking for. Everybody see that? Make sure you're reading carefully and looking at the picture carefully for some of these when they don't indicate where the angle is. So to calculate this angle B, I'm going to use tangent inverse of opposite over adjacent, and bada boom, bada bing, out spits 36.29. Does this feel okay so far? Again, you probably figured a lot of this stuff out from the homework because I assigned problems that I shouldn't have. Oopsie-daisy. You guys will forgive me because it wasn't due today. You know, you just were aggravated last night maybe, but that's not the end of the world. Probably a lot of us figured most of them out even without having gone through it. Maybe. The crowning achievement in my use of clip art. A rescue helicopter is hovering 156 meters above the sea. It is dark and the helicopter is shining a light straight down onto the surface of the sea. If the diameter of the cone formed by the beam of light is 140 meters, what is the angle at the apex of the cone? So there's my helicopter. There's my cone of light. We know that LO is 140. So LN, for example, is 70. Because this is an isosceles triangle, LMO, I know that if I split it in half, that's going to bisect the base and bisect the angle at the apex. That's what I'm going to do to calculate that angle. So I'm going to calculate the angle LMN and then multiply it by 2. You could have also used the law of sines to do this. That wouldn't be wrong to do, but seems easier to me to just do this, use SOHCAHTOA, and multiply by 2. A lot less aggravation to me. So here we go. To find this angle, we'll do tangent inverse and then multiply it by 2. Again, I know that this MN bisects that angle because this is an isosceles triangle. Have to have the isosceles triangle part for me to know there's an angle bisector there. Everybody's okay with that? Okay. We've seen that a couple of times, and I've been hammering it, mostly because I saw first semester, maybe it was even this semester, I don't remember when it was, people doing bisectors when they aren't really bisectors. So I just want to hammer that point a little bit. And that's it for that section. Woo! Section to do. We did make this choice last time. Hey, everybody has regrets, you know?
In all honesty, I feel like we probably should have learned that section so we were more prepared for homework and related.
Oh, FYI, in case you hadn't noticed, the homework due date, I changed rather than being this Sunday to the Sunday after break. So there won't be a homework check this coming Sunday. It'll be the Sunday at the end of break.
What do we have to go up to?
I think there's only 32 problems in the homework set. But, you know, if it saves you a little bit of aggravation, it's no skin off my nose, right? It's got to get graded sometime, whether it's this Sunday or next Sunday. It doesn't make much to me. If it makes everybody a little bit happier to do it next Sunday, I'm happy to do it next Sunday. All right, the last section is volumes and surface areas. Anytime you want to go here, computer. You gonna do something?
It's thinking.
Yeah, I broke it in good. All right, some common volume and surface area formulas are.
Oh my
Wait, are we supposed to say it now?
No, they're supposed to be coming. There's just a lot of them. But my computer is like just on protest right now. It just doesn't want to do anything.
He wants to think. Just let him think for like 10 seconds.
It doesn't need to think. This is not that hard.
If you're going to do it, it's very hard.
No, like it's a PowerPoint. It shouldn't take. It's because Microsoft has gone and like redefined how they're doing PowerPoint like a million times to be. Oh, we're gonna make it a better interface. It just makes it run slower. It's like it was better before when there wasn't like a presenter view and a other view and like there's all these different screens that have to come up, and now it's just lagging. Oh, and now I've probably pressed times. Here are our formulas, at least for the moment. I think it's going to blank out again because I think it's still lagging. But so cuboid, length times width times height, right? Everybody probably remembers that. The surface area, how in the God's name do you get this? Well, what we do is we unfold the cube. There's 6 sides to it, right? You have 2 sides that were length times width. 2 sides that were like length times, and then 2 sides that were length times width, right? When you unfold the cube into a net, that's what we call it when you take a 3D figure and you unfold it into like a 2-dimensional space. A right pyramid, that is one with a rectangular or square base. So the volume is just 1/3 base times height. The surface area is going to be the area of the base plus the area of each triangular face. Keep in mind, if the base is not a square, those triangular faces won't necessarily be the same size, right? If the base is a rectangle, you're going to have 2 different sized pairs of triangles in there. The cone, the volume is 1/3 pi r squared h. Notice that pi r squared is just the area of a circle, which is the base of a cone, so it's really still 1/3 base times height. Just FYI. The surface area for a cone is pi r L plus pi r squared. The L there is the slant edge. So how in the heck do we get that? Well, if you unfold a cone, like you clip along that slant edge and unfold it, what you get is a rectangle, right? The rectangle, one side has got to match the perimeter of the circle. That's the pi r part. And then the L is the height of the thing. So a sphere, the volume is 4/3 pi r cubed, and the surface area is 4 pi r squared. I'm not going to talk about how you do that because it's actually kind of complicated. how you derive that formula, because it's not at all obvious in looking at it. But a hemisphere is just half of a sphere, right? So the volume is cut in half. The surface area, though, depends on whether you're counting the base of the hemisphere as a surface or not, right? So like you have a dome and it sits on the ground and you're going to paint the dome, you don't care about the circle at the bottom. That would be the 2 pi r squared where there's no base. But if you had like, like a lampshade or something, at a hemispherical lampshade that was sitting on like a stick or something, there you would want to count that as a surface, because that's like, a surface. So we have 2 different versions there. You have to be a little bit careful about which one you want to use depending on the circumstance. A right prism, the volume is just the area of the base times the height. So remember, a prism is 2 parallel bases that are connected by rectangles. So the area of that base, maybe it's triangle, maybe it's a rectangle, maybe it's a pentagon. Well, a regular pentagon, it probably wouldn't be something other than that. It wouldn't give you a non-regular figure there. That would be too much. So the surface area is going to be the bases, and then a rectangle, and there's, for each of the parallel ones. So the number of sides on your base will be how many rectangles you have. So like if you have triangles as bases, you'll have 3 rectangles. If you have squares, you'll have 4 rectangles. If you had a pentagon, you'd have 5 rectangles, etc. A cylinder, the volume is pi r squared h. Again, pi r squared is just the base, the area of the base, since the base of a cylinder is a circle. So it's really the same as the prism formula. And then the surface area for your cylinder is 2 pi r h if you have no base. So like if you have like a silo or something. Or no, that's more like like an empty tube, like a pipe. That's a cylinder with no base, right? Just like an empty pipe. Not like a smoking pipe, but like a plumbing pipe. And then you have, so that is just the rectangular part, right? Like if you snip along the cylinder and you unfold, you have a rectangle and a circle. And then with the bases, you have 2 pi r h plus the 2 pi r squared. Everybody okay on these? I just kind of talked through what the formulas were. These would all be given to you. You don't have to worry about memorizing things like this. Let's do some examples. 3 tennis balls are packed in a cylindrical container, just touching the sides, top, and bottom of the container. The diameter of a tennis ball is 6.7 centimeters. Write down the internal height of the container, the diameter of the container, calculate the volume of the container, giving your answer rounded to the nearest whole number. The curved surface of the cylinder is made of plastic, and the top and bottom are made of metal. Calculate the area of plastic used and the area of metal used. Everybody ready to go? Okay. So the internal height of the container, what's that going to be? 6.7 times 3, right? We just stack up 3 tennis balls and they fit exactly the inside of the container. The diameter of each tennis ball is 6.7, so 6.7 times 3. The diameter of the container is 6.7. It's got to be the same as the sphere. Remember, the balls are touching exactly the top and bottom of the cylinder and the sides of the cylinder. That was easy. Calculate the volume, rounded to the nearest whole number. So your volume of a cylinder is pi r squared h. So that's 3.35 squared plus 20.1. Where's the 3.35 coming from? Half of the 6.7, right? Half the diameter is the radius. Cool there? Okay. And then the area of plastic used, that's just the lateral surface area. So that's the 2 pi r h part from the surface area formula, or the cylinder with no bases. So I fill that in. There's that. And then the metal is just the base is the top and bottom. So that's 2 circles. So 2 pi r squared is that. Questions so far? No big deal, right? We're just basically plugging stuff into formulas, right? The hardest part is maybe seeing like how to fill in the lengths or whatever to fill in the numbers into the formula, but basically just using formulas. Okay. Next one up. The base of a prism is a regular hexagon with sides of 3.5 centimeters. The length of the prism is 19 centimeters. Calculate the volume of the prism and say the prism is to be made of a flexible plastic and sold as a pencil case. Calculate the area of material needed for each case, i.e. just what's the surface area, right? Okay. So I'll start by drawing myself a picture. So here's my prism. Notice the bases here are regular hexagons. We have 19.5 centimeters between those hexagonal bases, and each side of that hexagon is 30 or 3.5. Remember, regular means all the sides are the same and all the internal angles are the same. So like an equilateral triangle is the same as a regular triangle. A square is the same as a regular quadrilateral. We don't have a special name for other regular figures. We just call them regular pentagon or hexagon or whatever. So to calculate the volume, we need the area of that hexagon times the 19, right? So the tricky part is calculating the area of that regular hexagon. So what I did is I took that regular hexagon and divided it into 6 equilateral triangles. Where the side length is 3.5 for this side. And because it's equilateral, I know that's also 3.5 for those sides. Oh, hold on a second. How did I know that this was going to be a 60-degree angle? Well, this spot here is 360, right? Because it's a circle. I divided it into 6 angles that are all identically sized. So I knew that this apex angle was 60 degrees. Is everybody okay with that? I think you do this calculation in honors geometry, but I know that was a long time ago and maybe we don't really remember doing this. I believe it's a hard thing that you do in honors geometry, or considered a hard thing, calculating the areas for these regular figures. But that's what I needed. So now that I have that, I can use my area formula for a triangle using sine, so 1/2 base times height, or I'm sorry, 1/2 AB sine C is what we called that. So it's 3.5, 3.5, and then the included angle. So the area of my triangle is about 5.3. So the area of the base of my hexagon is 6 times that. And the volume of my prism is then 6 times the 5.3 times the 19, or 604 and change. Everybody okay there? Okay. To get the surface area then, well, this is my rectangular face. I have 6 of these identically sized, right? So my surface area is 2 bases and 6 rectangles. The base we know was 5.3 from the previous calculation. I'm sorry, it was 6 times 5.3 from the previous calculation. And the area for the rectangle is 19 times 3.5. So my surface area is 2 times 6 times 5.3 plus 6 times 19 times 30 or 3.5, which gives me about 562 and change. So I try really hard to use subscripts here on things so that we don't get too turned around, like the base, like what base or figure are we talking about? Is it like the base for the rectangle, or is it an area of a base? So I try really hard to like use some subscripts so I don't get confused, or it's not confusing when you go back and look at these things. I'd encourage you to do the same with your work, but if you're fine, you can keep stuff straight without them, that's fine too, but Lord knows if it's a complicated problem, it helps to label things well. I think this is our last example here, if I recall. So let's say we have a lampshade. It's made from a cone of glass with a glass hemisphere as the base. The slant height of the cone is 29, and the diameter of the hemisphere is 11. Calculate the surface area of the lampshade and the volume of the lampshade. So this lampshade's like a lava lamp. Have you guys seen a lava lamp before? So this cone is actually sitting flush on top of the hemisphere. So the surface is just the lateral surface for the cone, no circle, and the hemisphere, no circle on the top, right? Is everybody okay from the context of the problem, how I came up with that? It's not totally clear from the picture because it was hard to draw that intelligently with the two smushed together. Let's do that surface area. So we have the area of that shade is going to be the cone plus the hemisphere. So the lateral surface area of the cone is the pi RL, and the hemisphere with no base is 2 pi R. I have everything I need in the picture, so I'm just plugging the numbers in. Everybody cool there? Okay. To get the volume then, I'm just going to say the volume of the lamp is the cone plus the hemisphere. So the volume for a cone is 1/3 pi r squared h, and the volume for a hemisphere is 2/3 pi r cubed. And again, the only thing I don't know is the height, so I'm going to have to find that first. So I use this calculation triangle here, and I can just use the Pythagorean theorem to find the height. And then I just plugged in the values into my two formulas and added them together to get the total volume. Is that okay with you guys? That's it. High five. What's up, bro?
I have a different question. So, like, with a right pyramid, you need to use the base. What is the base? Is that like the side times side?
So the base for a right pyramid could be a lot of different things. It could be a triangle. It could be a rectangle. It could be a square.
Like a square.
Okay.
So would it just be like the volume of the square?
So.
I'm like,
Are you talking about the surface area of a right pyramid with a square base, or the volume?
The volume right now.
So the volume is just 1/3 base times height.
And then what's the base figure?
The area of the base.
Okay, that's a...
Yeah,
okay.
so the capital B in that formula is the area of the base, as opposed to just like a lowercase b, which is like a side length of something. Yeah, no problem, my man.